All right, let's continue. Earlier, we mentioned that under very strict conditions, the speed we should use is the true airspeed. And the density should be the density of the free stream atmosphere at the local altitude, right? But if we consider it from a mechanical equivalence perspective, we say that actually, when an aircraft is flying, we are just assuming, after eliminating various errors, that the equivalent dynamic pressure is actually a concept of completely equivalent dynamic pressure, right? So in this context, if we consider the dynamic pressure to be the same, then what should the corresponding density be if we want to use equivalent airspeed? The standard reference is the density of the standard atmosphere at sea level, right? Do you still remember what the value is? .25 kilograms per cubic meter. So, at the same time, in the Bernoulli equation, we sometimes mention that this dynamic pressure and that dynamic pressure are completely consistent. Therefore, for convenience in calculations, we can also use the equivalent airspeed multiplied by 1.25 to obtain the local dynamic pressure. So this is the content we want to explain regarding dynamic pressure. Next, let's examine some issues more related to our flight, such as when the aircraft is climbing during flight. As our flight altitude continues to increase, recall what we discussed earlier about the standard atmosphere. What happens to the atmospheric density? The atmospheric density decreases, right? So, if we want to maintain the lift of the aircraft unchanged at this point, what should we do? Do we have any methods through our lift formula? Increase the lift coefficient. All right, we've talked a lot. So let me first ask everyone, what corresponds to dynamic pressure? Increase the dynamic pressure, right? And then, how does our aircraft increase the wing area? Finally, start the engine. During normal flight, the wing of the aircraft, you shouldn't be able to change it. So, when we are controlling the aircraft, there is no option to have a larger wing area in the state of normal flight. And then, what else is there? We should be able to choose to increase the lift coefficient of the aircraft. So how exactly do we do that? Correspondingly, if we want to increase the lift coefficient, we should pull back on the control stick, which increases the aircraft's lift coefficient. Therefore, under normal circumstances, in order to maintain the aircraft's lift, when altitude increases and density decreases, we can choose to accelerate or increase the aircraft's lift coefficient. All right, here we mentioned that we are dealing with speed acceleration. What kind of speed are we increasing? Or, after descending, are we increasing the airspeed, and what kind of airspeed is that? What kind of airspeed is this? When we do a physical analysis in this lift formula, what kind of airspeed are we using? It's true airspeed, right? Yes, that's correct. Now, let's consider the situation. During actual flight, when we fly general aviation aircraft, do we have instruments that display true airspeed? No, right? So what kind of airspeed is displayed by our aircraft at this time? It's airspeed, specifically indicated airspeed. From a strict perspective, what does it reflect? Which quantity is it? When the indicated airspeed is the same, what quantity remains consistent during the flight process? Right! We previously emphasized a fundamental concept about our airspeed indicator. Exact. The core of what the airspeed indicator shows is actually a change in dynamic pressure. Yaktang, correct? All right. Because during our actual flight process, we look at the indicated airspeed on the airspeed indicator. When the indicated airspeed remains unchanged, it reflects that the dynamic pressure is unchanged. All right, let me ask you, if during the process of the aircraft climbing, we ignore the impact of measurement errors, if my aircraft maintains a constant lift system during the climb, then how should the indicated airspeed be during the climb? Let me repeat. At this time, I am controlling the aircraft to climb. I keep the reading on the airspeed indicator unchanged. And at the same time, I do not want to operate, keeping the lift coefficient unchanged. Then at this time, how should the indicated airspeed be for the aircraft? Hello, I am Han Kuo Yu. May I ask if you have any intentions? I want to keep the total lift unchanged. I want the total lift to remain unchanged. If that is indeed the situation, we should carefully consider the necessary actions to address it. This could involve assessing the current conditions, gathering additional information, and making well-informed decisions to ensure the most favorable outcome. 1. Small, 1 large. This is a concept directly related to our aircraft during flight. All right, then we say dynamic pressure. We say what we get is just the airspeed, which is a direct feedback of dynamic pressure, right? So the airspeed remains unchanged. The dynamic pressure remains unchanged, correct? Therefore, during the climbing process, or actually, when we are not manipulating the control stick and when climbing at a constant indicated airspeed, the dynamic pressure should remain unchanged. Or conversely, if we maintain the dynamic pressure unchanged while climbing, then only the airspeed, then only they should remain completely unchanged, right? And at this time, which airspeed changes? Is this the true airspeed? You understand this relationship now, right? All right. So this is about the effect of changes in aircraft altitude and perceived altitude on lift. Now let's switch to another topic. Let's say our aircraft takes off from an airport during a hot summer. At this time, we say that a significant parameter affected by high temperature and high humidity is the density altitude. It increases, right? Do you remember what density altitude is? How can I explain density altitude in layman's terms? Density altitude refers to the actual atmospheric density we are experiencing. Yes, exactly. You look it up in the standard master table, and whatever altitude you find is the altitude it is. Remember this. This is the layman's way of explaining density altitude. All right, so when we say an aircraft is flying in a high density altitude area, it means that its flexibility, relatively speaking, is in a smaller state. When taking off, all right, when we lift off, assuming our liftoff sound coefficient is fixed. All right. So at this point, what should our liftoff indicated airspeed be? Let's repeat again. We are taking off from an airport at a high density altitude. Relatively speaking, it's smaller, and then the weight of the aircraft hasn't changed, meaning the total lift required is the same. At the same time, when our aircraft is flying, the attitude corresponding to takeoff, or the angle relative to the airflow, is the same. So the lift coefficient is also the same. Now I want to ask, what should your indicated airspeed be at liftoff? At liftoff, the indicated airspeed should remain unchanged, right? Because the weight hasn't changed, the lift hasn't changed, and the lift coefficient hasn't changed. Naturally, the dynamic pressure hasn't changed, so the indicated airspeed at liftoff should remain unchanged, correct? All right, then I'll ask you the next question. What about the true airspeed at liftoff? It's a nightly alarm. Scissors. Ah, right. How about the speed in a vacuum? Many of our classmates got it right, didn't they? The speed in a vacuum increases due to the decrease in density, right? Okay, let's assume our plane is in a no-wind condition, completely calm. When you accelerate from a standstill to your takeoff speed, what speed are we talking about at that point? The speed we accelerate to relative to the ground should be ground speed. But what I want to talk about is airspeed, because I've already assumed a no wind condition. What kind of action is this? The speed I should accelerate to relative to the ground should be the same as the true airspeed, right? Because I'm not considering the wind. There's no wind. So the speed relative to the wind and the speed relative to the ground are exactly the same, right? There's no relative motion between the wind and the ground. So the speed I'm accelerating to at this moment should be the true airspeed. However, as the density altitude increases, the corresponding true airspeed needs to increase. At this point, how should the aircraft's takeoff distance be? At this point, the aircraft's takeoff distance should increase, right? Because you need to accelerate to a higher speed. Naturally, you will need a longer takeoff distance. This is an important impact on our takeoff performance when analyzing changes in density altitude from a physiological formula perspective. Additionally, there's a very simple point, which I think doesn't need much explanation. That is, when the airspeed directly increases by n times then. It should be an n squared increase, right? If we want to maintain the lift with the total lift unchanged, the lift coefficient should be in a relationship of 1 over n squared, correct? All right. With this simple formula analysis, we can derive a lot of such information. For those who didn't understand, I hope you will review the course video after class to clarify this point, as it is a very important fundamental concept for our flight safety. All right, after finishing the first part, let's move on to the second part, which covers some related parameters and terms of Type 1. In fact, it doesn't have much technical content. It's just something you need to memorize. However, when we are making some academic descriptions, these terms are necessary. Right? For example, when you're discussing with others and you mention the teacher who talks about the principles of flight, you can just directly say it and that's it, right? However, if you don't use this term, you can't just say anything. You'd have to specify not only the teacher of the principles of flight, but also that they are from Beihang University and which batch they teach, and then say that this teacher is terrible. So you have to say a very long sentence, right? It makes it unclear for the listener. Well, whereas if you just say, send it over, everyone understands immediately. The same applies when we are describing an airplane. If you want to use a very long sentence to describe something you want, but on one hand, it might be hard to understand, and on the other hand, it might make you seem inexperienced, right? So, we need to use an accurate and simple term to describe certain aspects of the airplane, hoping we can remember it. The first concept is called airfoil. In the West, in the United States, it's called an airfoil, and in the UK, it's called an aerofoil. Both are the same term, or we refer to it as an airfoil. Corresponding to an airplane, if we take its wings and cut them into sections, the shape of the cross-section is what we call the airfoil. Additionally, in some sailboats, propellers, helicopter rotors, and turbines, the shape of their cross-sections is also called an airfoil. Next, we take this airfoil out for analysis and draw it here. So, what should the foremost position of the airfoil be called? Very good. You remembered the English term well. And what about the back? Very good, very good. You remembered all of this, right? The leading edge and the trailing edge. If I draw a line between them. It's called the chord line. In English, it's called the chord line. This is called the chord line, represented by the letter C, and its length is referred to as the chord length. And then, we can perform another process on this type. Can we? Draw countless tangent circles along the leading edge to the trailing edge of this airfoil, tangent to both the upper and lower surfaces. At this point, the centers of these countless tangent circles can be connected to form an arc. We give this arc a specific name. We call it the mean camber line in English. However, at the same time, if we calculate this line using this method, it can be quite troublesome. So what do we do sometimes? In engineering, we tend to take shortcuts. When we take shortcuts, we directly average the upper and lower surfaces at each position from front to back, which can also give us an approximate line that doesn't differ too much. In the engineering field, we usually do it this way, and what we obtain is the mean camber line. Once we have the mean camber line, it has a certain relative relationship with the leading edge. Since it is a curved line that arches up, naturally, there will be a point, the point where it arches the most. We call this the point of maximum camber. The specific position where it arches up and the distance between this point and the chord line is what we call the maximum camber. By dividing this maximum camber by the chord length, we obtain a dimensionless quantity called the relative camber. Additionally, the maximum camber has a specific position along the chord line, which we refer to as the location of maximum camber. We also use the length at this position to define it. By dividing by the entire chord length, we obtain a relative percentage value. This is the definition of maximum camber, relative camber, and the location of maximum camber. Additionally, we have a definition for thickness. What is thickness? Thickness refers to the vertical distance between the upper and lower surfaces. This refers to a circle inscribed within the profile, corresponding to a diameter, which is called the thickness. The maximum thickness is the diameter of the largest such circle. Similarly, you can determine it by directly using the coordinate difference between the upper and lower surfaces. The position of the maximum thickness is used to represent it, and this is called the maximum thickness. In engineering, we often use what is called the relative maximum thickness, which is the specific value of this thickness divided by the chord length. Similarly, we also have the relative position of the maximum thickness, which is the length corresponding to the position of the maximum thickness along the chord line, divided by the chord length, and it is also expressed as a percentage. This is the relative thickness. Finally, there is one more parameter, which is the principal of all these, the first circle. That is to say, this circle is tangent to both the upper and lower angles, and also passes through the leading edge. We call the radius of this circle the leading edge radius. Using these parameters, we can describe the shape of a specific airfoil. Of course, there are more complex ways to describe it, but they have a relatively weaker impact. Therefore, pilots don't need to pay much attention to them. However, I hope we can form an impression of these parameters in our minds and understand roughly what they refer to. Here, the most important things we need to understand are one is the P, and the other is the consequence. Because changes in camber and thickness have a significant impact on the driving force of the airfoil. In this class, due to limited time, we only briefly went over it. I hope students will remember the specific definitions after class. All right, so this is a description of the shape. Once we have the shape, we also need to describe the aerodynamic behavior on its surface. For a two-dimensional airfoil, it also has its relative relationship with the airflow. Here, we refer to the angle between the two-dimensional airfoil chord line and the direction of the incoming flow as the angle of attack of the two-dimensional airfoil. Note that it is the angle between the two-dimensional chord line and the direction of the incoming flow, which we call the zero angle. At this point, we say that because a normal airfoil has an angle of attack and a velocity, there should be a resultant aerodynamic force acting on it, right? So this resultant aerodynamic force, it has a specific point of action, which we refer to as the center of pressure, like represented by center of pressure, or used to express it. It represents the point of action of the resultant aerodynamic force. Now, if I use something to fix it, and this shape is fixed exactly at this point, allowing it to rotate around this point, I ask you at this moment, under this apex angle, if the shape is fixed, will it rotate? No, I fixed the shape at the center of pressure at this point. Will it rotate? It will not rotate, right? Because the resultant force passes through this point without any torque, so it cannot rotate. This is a very important example of the center of pressure. Now, after obtaining the resultant aerodynamic force, we need to determine our lift and drag. In which direction should the lift be? It is exactly the same as our whole aircraft definition. The lift direction of the 2v1 type should be perpendicular to the direction of the incoming flow. In the vertical direction, it points straight up. Similarly, the drag should be decomposed along the direction parallel to the flow. And then the horizontal backward direction is the direction of the drag. All of the above content is purely definitional, something to be memorized without any reasoning behind it. Because the earliest researchers of aircraft defined it this way. When we want to explain or teach others, we need to be clear. We need to know the names of these things. We can't just say the front of the chicken and the back of the chicken, right? We need to say leading edge and trailing edge, correct? We also can't just say the line connecting the front and back. It should be called the chord line, okay? That's all we have to say about definitions. Next, let's take a look at the flow characteristics of a two-dimensional airfoil. Here, we present a symmetrical airfoil, and then I will change the angle of attack of this airfoil. So, what information can we observe here? The black line. These are streamlines. And after passing through this reverse flow, notice how the distance between them changes, right? So if the streamlines are squeezed together, what does that indicate?
Recorded song. When the flow speed increases, the pressure decreases. On the other hand, if something pushes it open, the flow slows down and the pressure increases. In this diagram, the pressure is also represented using colors. Red indicates areas with more higher pressure, while blue indicates areas with more lower pressure. The streamlines have spread out, right? That means the flow has slowed down, so the pressure is higher in this area. Here the streamlines are denser and packed together, so the flow speed is higher and the pressure is lower. Next, we'll change the angle of attack to see how the flow field changes accordingly. This is the case with a positive angle of attack. This one is with a compound angle of attack. What we're showing below is the distribution of surface forces after the change. The length of the lines represents the magnitude of the force. The red lines indicate pressure, and the blue ones, we refer to them as suction. We'll explain later why it's called suction. Okay, so here, let's look back again. If we increase the size of this special shaped corner, we get the shape of the flow field. We say that this is a symmetrical stealth. When the angle of attack is 0, what should be the lift on it? For a symmetric airfoil, what should the lift be when the angle of attack is 0? Why is that? Because the pressure distribution on the upper and lower surfaces is exactly the same. There's no pressure difference, right? So it can't generate lift. Therefore, the lift must be 0 for a symmetric airfoil. But once it has a positive angle of attack, then it should start generating lift, right? Let's take a look at the flow field. When there's a positive angle of attack, the flow moves like this from front to back. Let's pay attention to the flow direction in this region before the leading edge. What is it like? Hold on, let's look at the direction of streamlines. What do you see? It's flowing upward, right? So here I'll mark it as upwash refers to upward flow. Why is it called upwash? Because the English term is wash up. In Chinese, it's shangxi. Why wash is used? The coiner is dead, can't change it. All right. So when the airflow around the airfoil essentially passes over it and then moves on to the next stage of flow, we can observe which direction it's going in, besides just backward. It's moving downward, right? So this downward flow, we're about to analyze this downward flow. So the airflow has changed from moving upward to moving downward. This indicates that the momentum of the air has changed. And what can cause a change in momentum? Only a force can cause a change in momentum, right? So that means an upward lift is generated on the wing, correct? Because forces always come in pairs. By changing the airflow from upward to downward, a downward force is applied to the airflow. Naturally, the airflow then applies an upward force to the wing, or the airfoil. This is the momentum theory we use to explain lift. At the same time, we can also observe the change in pressure distribution. At the lower and front part of the airfoil, this area appears red, indicating that the flow field is separated. So the pressure, there's an increase in pressure in that region, right? And then, as the flow continues, when it reaches the upper surface, particularly at the front and upper part, we can see that the streamlines are narrowing, right? This area appears blue, indicating an increase in flow speed and a decrease in pressure. So below, where it's red, the pressure is high. Above, where it's blue, the pressure is low. This pressure difference between the top and bottom creates an upward lift force. This is a specific way to describe how lift is generated in a two-dimensional airfoil. Now, if we only use colors and streamlines to represent this, it may not be very precise. So sometimes, we also use other quantitative methods to express it more accurately. Here we introduce a concept called the pressure coefficient. So, what exactly is the pressure coefficient? Let's take a look. The pressure coefficient is denoted by CPE, and specifically, it refers to a certain point at a given location. It is defined as the difference between the local pressure at that point and the atmospheric pressure at infinity divided by the dynamic pressure of the flow. This is what we call the pressure coefficient. The reason we use the pressure coefficient is because it eliminates the dynamic pressure, making it a pure coefficient. At this point, when similarity conditions are met, meaning the angle of attack and side slip angle are the same, then, when the Mach number and Reynolds number are similar, the pressure coefficient, or CP, remains basically unchanged. In this way, we can use it to bridge the relationship from a small model to a full-scale aircraft. This is what we refer to as the pressure coefficient. For pilots, the pressure coefficient isn't a particularly important concept. Here, it's just introduced to give everyone a basic understanding. Now, with the pressure coefficient, we can define certain special points within the flow field. The first point we refer to is called the stagnation point. So, what is a stagnation point? A stagnation point refers to a point within the flow field where the flow velocity becomes 0. This point is what we call the stagnation point. So what should the pressure coefficient be at the stagnation point? The pressure coefficient should be equal to 1. Why is it 1? right? The total pressure P0 equals 1/2 RHO V squared plus P, correct? This RO can also refer to the free stream RHO, referring to conditions at infinity. So when there's a point where the velocity V becomes 0, what does that mean? It means that the local pressure equals the total pressure, right? At that point, if we subtract P from P0, this here is just P, isn't it? Then what we're left with is 1/2 RHO times V squared. Then, if we divide by the denominator, 1/2 RHO times V squared, doesn't that just equal 1? So, at the critical point where the flow velocity is 0, the pressure coefficient should be equal to 1. In addition, if at a certain point the flow velocity is greater than the free stream velocity far upstream, then that means when the velocity increases at a certain point, it's no longer P infinity because we're referring to a specific local position. So at that point, when the velocity increases, what happens to the pressure? When flow velocity increases, what happens to pressure by Bernoulli's principle? The pressure decreases, right? All right. So for a given velocity at a certain location, if that velocity is already greater than the free stream velocity upstream, that is, if it's a process of acceleration, then how does the local pressure compare to the free stream pressure? Is it higher or lower? When the flow velocity increases, what happens to the pressure? It should decrease, right? So in this case, the force corresponding to this situation is what we refer to as suction. This suction refers to the local force relative to the pressure far upstream. When there's a region where the flow velocity is higher than that of the free stream upstream, the corresponding force is what we call suction. Now, in the context of suction, let's take a look at the pressure coefficient. Now, since the velocity at this point is undoubtedly higher than the free stream velocity upstream, right? Then, corresponding to the local pressure coefficient at this point, because the pressure here is certainly lower than the pressure far upstream, the numerator in the pressure coefficient formula should be a positive number. The local pressure being lower than the free stream pressure means it should be a negative value, right? So, when it comes to the pressure coefficient, it should be a negative number. This region, then, is referred to as a suction area. With this concept in mind, we can use it to observe the flow field around the entire airfoil and understand how the forces are distributed. Alright, before we look at the specific surface force distribution on this particular airfoil, let's first review what our two-dimensional flow looks like. For a typical airfoil, at a relatively small positive angle of attack, which of the following descriptions about the surrounding flow field are correct? Note that this is a multiple choice question. Please take a look, and you have 1 minute.
Okay.
Alright, time's up. So how did it go? What should we choose, Teacher Lee? Most of the students got it right. This is actually just two different explanations of lift, completely equivalent ways of explaining it. If we start from Bernoulli's principle, we say that the flow speed is higher on the upper surface, so the pressure is lower than on the lower surface. Lower flow speed means higher pressure, right? At the same time, how else can we explain lift? We can use the principle of momentum to explain it. So when the airfoil has a positive angle of attack, in front of it, which direction should the airflow go? Upward, right? But after passing over the airfoil, the flow direction turns downward. Whenever the momentum of any moving object changes, there must be a force acting on it for that change to occur. The air was originally flowing upward, but then it changed to flow downward, so there must be a force acting in the downward direction. It was originally moving upward, but then it started moving downward. For it to move downward, there must be a downward force, right? So who provides this downward force? It's the wing that applies a downward force on the air. Therefore, the air applies an equal and opposite upward force on the wing, and that is the lift we need. All right, if anyone got it wrong, I suggest reviewing the related concepts. Then we'll demonstrate it to everyone with an experiment.
Combinations of favorable and unfavorable gradients occur over the surfaces of a dynamic shape. This air level has a maximum fitness of 12% of the cordless and located about a quarter of a client police. Just take a look. It's not translated by me. Your seniors did. These tubes are connected to the model alternately from the top and bottom.
So here, this is essentially a type of side pressure wind tunnel. How does it fundamentally work? As we can observe, these tubes below are all specifically U-shaped tubes, and one end of each U-tube is connected directly to the surface of the airfoil. This mechanism precisely demonstrates the functionality of the airfoil surface. The inner end? It's directly open to the atmosphere. All right, so if the end of the connecting tube has a very low pressure, meaning the pressure is lower than atmospheric pressure, what will happen to the liquid inside the tube? It will rise, you see, right? Just like when we use a syringe to draw something out. When we pull on the syringe, the liquid rises, doesn't it? So, according to this principle, the pressure at this point, we refer to it as suction, right? It's a force that pulls upward. That's where the concept of suction comes from. So what is the pressure it's being compared to? Where does that pressure come from? It's the pressure from the still atmosphere. Therefore, if the liquid rises on this side, it indicates suction. Conversely, if it's pressure instead, then it should move downward. So by observing the height of the liquid in the tube, what does a higher liquid level indicate? It means the pressure is lower, right? So does that correspond to a greater positive pressure or a greater suction? Greater suction, right? Also, why do we refer to it as suction here? In fact, this is very important in the actual process of aircraft manufacturing because the inner shell of an aircraft is basically in an airtight state. In this airtight condition, what is the approximate pressure inside the sealed inner shell? It's basically equal to the atmospheric pressure at rest at the local altitude. So, if an aircraft doesn't have enough structural strength in areas subjected to suction, for example, if the skin panels aren't firmly attached, then let me ask you, should the skin cave inward or bulge outward? What would happen? We say the pressure inside the aircraft is what kind of pressure? It's the pressure of still air, right? And the pressure corresponding to suction, what is it like? Compared to still air, it's lower, right? The pressure outside is lower, and the pressure inside is higher. So if the skin panel isn't firmly attached, what will happen? It would just burst open immediately, right? It gets sucked out, so that's what we call suction. All right? Now let's take a look at how the pressure on the surface changes as the angle of attack changes.
When the airfoil is set at 0 angle of attack, the pressure distribution creates this pattern on a single surface. The highest pressure appears at the leading edge, but it decreases as the airflow continues. and minimum pressure is reached near the thickest point. After this point, the pressure increases, creating an adverse pressure gradient all the way to the trailing edge. The airfoil is shaped so that at zero angle of attack, the pressure distribution on both surfaces is equal in magnitude. Increasing the angle of attack breaks this symmetry in the pressure distribution. The point of minimum pressure becomes more pronounced and shifts forward, increasing the severity of the adverse pressure gradient.
Alright, so this is the entire process of the experiment. At this point, we can use the liquid column to understand the local pressure, right? From this, we can determine how the lift changes. As for how to interpret this graph, we'll explain it to you in detail a bit later. So, besides using this method to observe changes in lift, we can also use the smoke wind tunnel setup to see how lift generally changes with variations in the angle of attack. By observing the smoke trails generated by the smoke generator, we can qualitatively analyze the flow behavior to some extent. Let's take a look at how the smoke trails change as the angle of attack varies. We can see that when the angle of attack is small, the smoke trails flow closely along the contoured surface. But as the angle of attack increases further, what do we observe? What starts to happen at the rear part? The airflow begins to separate, right? It no longer flows along the surface of the airfoil. As the angle of attack continues to increase, how does the separated region change? It moves forward. Exactly right. And what about the area? It also gets larger and larger, right? This illustrates how the surface airflow changes as the angle of attack increases. The effect caused by this kind of airflow separation is actually the stall phenomenon we mentioned earlier in the overview. However, stall is not the main focus of this lecture. Our focus remains on how the surface pressure distribution changes with variations in the angle of attack. Here, we will still use the pressure coefficient we discussed earlier. Then, we plot the negative pressure on the top and the positive pressure on the bottom, and we get a... This is a graph showing how the surface pressure distribution changes with variations in the angle of attack. On the top, a negative pressure coefficient indicates, does it represent positive pressure or suction? It represents suction, right? And on the bottom, it represents pressure, correct? All right. Now note that what we've drawn here is an asymmetric airfoil. So at a certain angle of attack, there is actually a pressure difference between the upper and lower surfaces. On the upper surface, do we see suction or pressure? Take a look at the pressure on the upper surface of the airfoil. Pay attention to what the values are like. They're negative, right? So the upper surface mainly shows suction. What about the lower surface? There's some suction as well, right? But it's not as strong. So together, the upper and lower surfaces form a difference in area, and this area difference essentially represents the lift. Now, let's take a look at what happens when the angle of attack increases. We can see after the angle of attack increases, how is the suction on the upper surface? In addition to the suction becoming stronger, what about the position of the peak suction point?
It moves forward along the chord line.
It starts to move forward, right? As the angle of attack continues to increase, we can observe this. The forward and upward movement becomes more and more pronounced, right? Alright, so we say that the pressure difference between the upper and lower surfaces corresponds directly to lift. Then we can see that as the angle of attack increases, where does the main contribution to lift come from? This is at a small angle of attack. As the angle increases, where does the additional lift come from? Where's it from? Mainly from the front part, right? The sharp peak at the leading edge actually contributes significantly to the increase in lift as the angle of attack increases. And as the angle of attack continues to increase, let's see what happens next. When it increases to a certain point, what phenomenon occurs next? What happens to the surface airflow we just saw in the video? Flow separation occurs, right? After separation, what kind of change do we observe in the pressure distribution? This is before separation, and this is after separation. What do we perhaps notice about the sharp peak? The sharp peak drops suddenly and dramatically, doesn't it? At the same time, you might wonder, what happens to the corresponding lift? Ah, the lift also decreases accordingly, right? But does the lift disappear completely? It doesn't disappear, right? There's still some lift. The region of positive pressure on the lower surface has basically remained unchanged. Did you notice? It's just the suction on the upper surface that disappears, right? So, when a large angle of attack causes separation, it mainly affects the sharp peak near the leading edge, but the positive pressure on the lower surface still remains. So there's still some lift being generated on the airfoil, but the total lift is reduced. Now, this is about observing the suction at the leading edge, looking at the suction peak at the front. This shows how it changes with the angle of attack. Sorry for taking a bit more time. Now, let's take a look at the next topic, the change in the stagnation point. So, what is the stagnation point like? Let's see. First, how is the stagnation point defined in terms of pressure coefficient? We define it using the pressure coefficient equal to 1, right? So the point where the pressure coefficient equals 1 corresponds to this point, correct? The green line represents the upper surface, right? So we can see that when there's no disturbance, the stagnation point is located on the upper surface, and it actually corresponds to this position. Then, let's look at what happens as we continue, and then take a look at this. This point here is key, and its pressure coefficient is 1. Now, if I were to ask everyone about this point, the point next to the stagnation point, this location, at this position, at this moment, its pressure is 0. So what can we say about the flow speed at this point? Its pressure coefficient is 0, the pressure is 0. Which value makes the pressure coefficient 0? The location where the pressure equals the atmospheric pressure at infinity. That's where the pressure coefficient is 0, right? So, what does it mean? It means the pressure at that point is the same as the atmospheric pressure far away. Now, what about the speed at that point? It's the same as the free stream velocity at that moment, right?